Picture this. Deep inside the darkness of our galaxy, a black hole is swallowing stars, and scientists now think these cosmic giants might be doing something far stranger than anyone expected. Recently, researchers studying the echoes of gravitational waves found a subtle pattern, tiny ringing signatures that shouldn't exist unless something is happening beyond the event horizon. And these patterns line up uncannily well with a bold idea called cosmological natural selection. Here's the mysterious part. The strange gravitational wave echoes scientists found resemble the same mathematical fingerprints we see in our universe's earliest moments, almost like a family resemblance passed down through generations of universes. It is not proof, not yet, but it is the closest hint we have ever seen that black holes might not be cosmic graves, but cosmic wombs. Leave a like and subscribe to the channel if you love the content, because tonight we are going to follow that trail of clues and explore the possibility that our universe itself may be the child of a black hole from a universe long gone. Get ready, we begin. Picture this for a moment. Every single black hole lurking in the darkness of space might be far more than just a cosmic monster devouring everything in its path. What if each one is actually giving birth to an entirely new universe? Not metaphorically, but literally creating a whole new reality with its own stars, galaxies, and perhaps even life. This sounds like science fiction, but it is actually a serious scientific hypothesis proposed by physicist Lee Smolin in the early 1990s. The idea is called cosmological natural selection, and it offers a radically different way to understand why our universe has the precise properties needed for galaxies, stars, and eventually us to exist. Instead of relying on luck or divine intervention to explain why the fundamental constants of physics are just right for life, Smolin suggested that universes might actually evolve through a process remarkably similar to biological evolution. The implications are staggering. If this hypothesis is correct, our entire universe was born from a black hole in some parent universe. Every black hole we observe today might be spawning countless daughter universes. These daughter universes would inherit slightly modified versions of our physical laws, and over countless generations, the multiverse would evolve to favor universes that are exceptionally good at making black holes. But here is where it gets truly fascinating. The same conditions that make a universe good at producing black holes also happen to make it good at producing life. Both require long-lived stars, complex chemistry with carbon and oxygen, and stable planetary systems. So perhaps we are not the product of blind chance or supernatural design, but rather the inevitable outcome of cosmic evolution. Think about what this means for just a second. The black hole at the center of our Milky Way galaxy, with its mass of roughly 4 million times that of our Sun, might have already created millions of new universes. Every stellar mass black hole scattered throughout the hundreds of billions of galaxies in our observable universe could be a doorway to a new cosmic reality. And if those daughter universes also make black holes, and those make more universes, the numbers become truly incomprehensible. We could be living in a multiverse that has been growing exponentially for an eternity, with our universe representing just one tiny twig on an infinitely branching cosmic tree. Before we dive deeper into cosmological natural selection, we need to understand the problem it is trying to solve. Our universe appears to be remarkably fine-tuned for the existence of complex structures and life. The fundamental constants of nature include things like the mass of the electron, the strength of gravity, the electromagnetic force, and the strong and weak nuclear forces. These values seem arbitrary. There is no obvious mathematical reason why they should have the specific values they do. Yet if you change any of them by even a tiny amount, the consequences would be catastrophic. Take the strong nuclear force as an example. This is the force that holds atomic nuclei together despite the electromagnetic repulsion between positively charged protons. If you reduce the strength of the strong force by just 2%, protons could not stick together to form nuclei heavier than hydrogen. No carbon, no oxygen, no complex chemistry, and obviously no life. On the other hand, if you increase the strong force by just 2% in the other direction, all the hydrogen in the universe would have been fused into helium and heavier elements shortly after the Big Bang. There would be no hydrogen left for water or for the long-term fuel that powers stars for billions of years. Again, no life. The electromagnetic force shows similar fine-tuning. If it were slightly stronger, electrons would be too tightly bound to atoms to participate in chemical reactions. If it were slightly weaker, atoms could not hold together at all. The ratio between the electromagnetic force and gravity is particularly crucial. Gravity needs to be much weaker than electromagnetism for stars to form and shine stably for billions of years. Change this ratio significantly, and stars either burn out in moments or never ignite at all. The cosmological constant, which drives the accelerating expansion of the universe, has a value that is extremely close to zero, but not quite. If it were slightly larger, the universe would have expanded so rapidly that matter could never clump together to form galaxies and stars. If it were negative instead of positive, the universe would have collapsed before any structure could form. The mass difference between neutrons and protons is another example. Neutrons are slightly heavier than protons, which means free neutrons decay into protons with a half-life of about 10 minutes. This is crucial for nuclear physics and the formation of atoms. Change this mass difference by a small amount and you completely alter the abundance of elements produced in the Big Bang and in stars. But the fine-tuning goes even deeper than just these individual constants. The ratios between different forces matter enormously. Consider the balance between the strength of gravity and the nuclear forces. If gravity were too strong relative to the nuclear forces, stars would collapse under their own weight before they could sustain nuclear fusion. If gravity were too weak, matter would never clump together to form stars in the first place. The expansion rate of the early universe also had to be exquisitely fine-tuned. If the universe had expanded slightly faster after the Big Bang, matter would have been too diluted to ever form galaxies. If it had expanded slightly slower, the universe would have recollapsed into a big crunch within its first few 100,000 years. Even the dimensionality of space seems fine-tuned. We live in a universe with 3 dimensions of space and 1 of time. Mathematical models show that stable atoms and planetary orbits cannot exist in universes with more or fewer spatial dimensions. In a universe with 4 spatial dimensions, for example, electrons would spiral into atomic nuclei and planets would either crash into their stars or fly off into space. Physicists have identified dozens of these apparent coincidences. The odds of all of them just happening to have life-permitting values by pure chance seem astronomically small. Some estimates suggest that if you randomly selected values for the fundamental constants, the probability of getting a universe capable of supporting life would be less than 1 in 10 to the power of several hundred. This is the fine-tuning problem. Why do we live in such an improbable universe? Why are the fundamental constants not just random numbers, but precisely calibrated values that allow for the existence of complex chemistry, stable stars, and eventually conscious observers like us? There are essentially 3 types of answers that have been proposed. The first answer is design. Perhaps an intelligent creator deliberately set the fundamental constants to values that would allow life to emerge. This is a theological answer rather than a scientific one, and while it cannot be ruled out, most scientists prefer explanations that do not require supernatural intervention. The second answer is the anthropic principle and the multiverse. If there are vast numbers of universes with different fundamental constants, then it is not surprising that some of them would have the right properties for life. We necessarily find ourselves in one of those rare life-permitting universes because we could not exist anywhere else. This is called the weak anthropic principle. It does not explain why life-permitting universes exist, but it does explain why we observe ourselves to be in one. The anthropic principle is philosophically troubling to many scientists because it seems to give up on finding a deeper explanation. It says the universe is the way it is because if it were not, we would not be here to ask the question. That feels circular and unsatisfying, even if it might be logically correct. The third answer is what Lee Smolin proposed with cosmological natural selection. Perhaps universes are not selected randomly, but rather they evolve over time to favour certain properties. Just as biological organisms evolve to become better adapted to their environments, perhaps universes evolve to become better at reproducing themselves. This is the idea we are going to explore in depth. But first we need to understand where it came from and what it really means. Lee Smolin is a theoretical physicist who has spent his career thinking about some of the deepest questions in physics. He has worked on quantum gravity, the nature of time, and the foundations of quantum mechanics. In the early 1990s, he was puzzling over the fine-tuning problem and became dissatisfied with both the design, explanation, and the pure anthropic explanation. Smolin was struck by a parallel between the fine-tuning problem in cosmology and the apparent design in biology. For most of human history, the complexity and apparent purposefulness of living organisms seemed to require a designer. How else could you explain the intricate structure of the eye, the wing, or the brain? Charles Darwin provided the answer in 1859 with his theory of evolution by natural selection. Complex biological structures are not designed, but rather emerge gradually through a process of random variation and differential reproduction. Organisms with beneficial traits tend to have more offspring, so those traits become more common over generations. Given enough time, this blind process can produce structures of stunning complexity and apparent design. Smolin wondered whether a similar process might explain cosmic fine-tuning. Could universes evolve through natural selection to have properties that favour certain outcomes? But for this to work, you would need universes to reproduce, to pass on their properties to offspring universes, and for those properties to vary slightly from generation to generation. This is where black holes enter the picture. Smolin was building on earlier speculative ideas by physicists like John Archibald Wheeler and Bryce DeWitt, who had suggested that black holes might give birth to new universes. The idea goes like this. According to general relativity, when matter collapses to form a black hole, it creates a region of space-time that is cut off from the outside universe by an event horizon. Nothing that crosses the event horizon can ever escape. At the center of the black hole is a singularity, a point where the density becomes infinite and the laws of physics break down. But most physicists believe that singularities are not real. They are artifacts indicating that general relativity is incomplete and needs to be replaced by a quantum theory of gravity at extreme densities. Several approaches to quantum gravity suggest that when matter collapses toward a singularity, quantum effects create a kind of bounce. Instead of collapsing to infinite density, the matter reaches a maximum density and then begins expanding again. This expanding region could be a new universe with its own Big Bang. From the outside, it still looks like a black hole, but on the inside, it is an entirely new cosmos with its own space and time. If this is correct, then every black hole in our universe could be creating a baby universe. And if those baby universes also form black holes, they would create their own baby universes, leading to an exponentially growing population of universes. Wheeler and DeWitt had proposed that the fundamental constants in these baby universes might be different from those in the parent universe. The extreme conditions during the black hole collapse and bounce might reset the values of the constants in unpredictable ways. Smolin added one crucial ingredient to this idea. He suggested that the constants would not be completely random in the baby universes, but rather would change only slightly from the parent values. This is analogous to genetic mutations in biology, which typically make small changes to an organism's DNA rather than completely scrambling it. If baby universes inherit slightly modified versions of their parents' fundamental constants, then a process of evolution by natural selection becomes inevitable. Universes that happen to have constants favoring the formation of many black holes will produce more offspring universes. Those offspring will tend to have similar constants and will also be good at making black holes. Over many generations, the population of all universes will shift toward configurations that maximize black hole production. This is cosmological natural selection. It is evolution operating not on genes and organisms, but on fundamental constants and universes. Now here is the truly remarkable part. What kinds of universes would be good at making black holes? In our universe, black holes form primarily when massive stars explode as supernovae at the end of their lives. To make lots of massive stars, you need lots of star formation in general. Star formation requires gas clouds to cool and collapse under gravity. The cooling is greatly enhanced by the presence of heavy elements like carbon and oxygen, which form molecules that radiate energy efficiently. So a universe that is good at making black holes needs to be good at making stars, which means it needs to be good at producing heavy elements through nuclear fusion in earlier generations of stars. It needs long-lived stars that can synthesize these elements over billions of years. It needs the right balance of nuclear reaction rates to produce carbon and oxygen in useful quantities. All of these same factors also happen to be essential for life. Life as we know it is based on carbon chemistry. It requires liquid water, which means oxygen combined with hydrogen. It requires stable environments around long-lived stars. It requires rocky planets made of heavy elements. So universes that are optimized for black hole production are also, as a side effect, conducive to life. This explains the fine-tuning without invoking the anthropic principle. We are not just lucky to live in a rare, life-friendly universe. We live in a universe that has been shaped by eons of cosmic evolution to be good at making black holes, and life emerges as a fortunate byproduct of that optimization. This is an elegant and beautiful idea, but is it actually true? To evaluate that, we need to examine each piece of the hypothesis carefully. The idea that black holes might create new universes is by far the most speculative part of cosmological natural selection. It requires physics beyond general relativity, specifically a theory of quantum gravity that we do not yet have. However, there are some intriguing theoretical hints that point in this direction. According to general relativity, when a massive star exhausts its nuclear fuel, it can no longer support itself against gravity. If the star is massive enough, nothing can stop the collapse. The star implodes, and its mass gets compressed into an ever smaller region. Within seconds, it forms a black hole. From the outside, a black hole appears as a spherical region of space from which nothing can escape. The boundary of this region is called the event horizon. Light emitted from inside the event horizon curves back and can never reach the outside universe. Time itself behaves strangely near a black hole. From the perspective of an outside observer, Anything falling toward the event horizon appears to slow down and freeze, never quite crossing the boundary. But from the perspective of something falling into the black hole, the journey continues past the event horizon. According to general relativity, the infalling matter would continue to compress, getting denser and denser until it reaches the singularity at the center. At the singularity, density becomes infinite, and the equations of general relativity produce nonsensical results like infinite curvature of space-time. Most physicists believe this indicates that general relativity breaks down at extreme densities. Just as Newton's laws of motion needed to be replaced by Einstein's relativity at high speeds, Einstein's general relativity likely needs to be replaced by a quantum theory of gravity at extreme densities approaching the Planck scale. Several approaches to quantum gravity suggest that singularities do not actually form. Instead, quantum effects introduce a kind of pressure or repulsion that prevents matter from collapsing all the way to a point. In loop quantum gravity, for example, the discrete structure of space at the Planck scale creates a maximum density beyond which matter cannot be compressed. When infalling matter reaches this maximum density, it bounces. But because it is trapped inside the event horizon, the bouncing matter cannot expand back into the original universe. Instead, it expands into a new region of space-time, effectively creating a new universe. Think of it like a bubble branching off from a larger structure. The original universe continues to exist, and the black hole remains from the perspective of observers in that universe. But attached to the black hole through the event horizon is a new expanding bubble of space-time, a baby universe with its own space and time. This baby universe would be completely cut off from the parent universe. No information or matter could pass between them. The baby universe would begin in an extremely hot, dense state, similar to our own Big Bang, and it would expand and cool, potentially forming its own stars, galaxies, and perhaps even black holes. This scenario is highly speculative, but it is supported by some calculations in loop quantum gravity and related approaches. Physicists have shown mathematically that bounces can occur in certain models of quantum gravity, and these bounces have the right properties to create new, expanding regions of space-time. One intriguing aspect of these models is that they might explain some puzzling features of our own universe. Our universe appears to have begun in an extremely smooth and uniform state. The cosmic microwave background radiation, the afterglow of the Big Bang, looks almost exactly the same in every direction in the sky, differing by only about 1 part in 100,000. In standard Big Bang cosmology, this uniformity is difficult to explain because different regions of the early universe were too far apart to have ever been in contact and equilibrated to the same temperature. Cosmologists usually invoke cosmic inflation, a period of exponentially rapid expansion in the first fraction of a second, to explain this smoothness. But if our universe formed from the collapse of matter in a parent universe, that matter would have already been processed and mixed in the parent universe. This could potentially explain why our universe started out so smooth without needing to invoke inflation. However, there are also serious objections to the idea that our universe came from a black hole. Black holes form from the chaotic collapse of stars, which involves shock waves, asymmetries, and turbulence. It is not obvious how such a messy process could give rise to the remarkably uniform early universe we observe. Another issue is that the interior of a black hole, as described by general relativity, does not look like an expanding universe. In a black hole, all matter is being pulled inexorably toward the central singularity. The geometry is one of contraction, not expansion. In our universe, space is expanding and galaxies are moving apart. These seem like very different situations. Some theorists, like Nikodem Poplawski, have tried to address this by invoking exotic physics like torsion in space-time, a twisting of the fabric of space that is not present in standard general relativity. Poplawski's models suggest that torsion could reverse the collapse and turn it into expansion inside the event horizon. These ideas are mathematically interesting, but they require modifications to general relativity that have not been experimentally confirmed. They remain highly speculative proposals rather than established physics. Observationally, we can look for signs that our universe might be inside a black hole. If we were in a rotating black hole, for example, space might have a preferred direction or show patterns of asymmetry. Cosmologists have searched for such effects in the cosmic microwave background and in the distribution of galaxies, but so far the universe appears to be remarkably isotropic, looking the same in all directions. This is evidence against the simplest versions of the universe in a black hole idea, though it does not rule out more sophisticated versions where the black hole is non-rotating and spherically symmetric. The bottom line is that the idea of universes forming inside black holes is an interesting theoretical possibility, but it is far from proven. It requires extensions to general relativity, specifically a theory of quantum gravity, that have not been experimentally confirmed. Most of the calculations are preliminary and involve many simplifying assumptions. For the purposes of evaluating cosmological natural selection, we have to treat this as a provisional assumption. If it turns out that black holes do not create baby universes, then the entire framework of cosmological natural selection collapses. The hypothesis lives or dies on this foundation. But let us continue assuming for now that black holes do create baby universes. The next question is whether those baby universes would have different fundamental constants from their parents, and if so, how different? For cosmological natural selection to work as an evolutionary process, baby universes must inherit fundamental constants that are similar but not identical to those of their parent universe. This is directly analogous to how biological offspring inherit genes from their parents with occasional small mutations. In biology, DNA is copied from parent to offspring with extremely high fidelity, but not perfect fidelity. Copying errors occur at a rate of roughly 1 mistake per billion base pairs copied. Additionally, environmental factors like radiation can cause mutations. These mutations are usually small, changing a single letter in the genetic code, or perhaps duplicating or deleting a short stretch of DNA. Large-scale mutations that completely scramble the genome are almost always fatal. Evolution proceeds through the accumulation of small changes that slightly modify the function of genes and proteins. Over time, these small changes can add up to dramatic differences between species, but any single mutation is relatively minor. For cosmological natural selection to work, something similar must happen with universes. The fundamental constants of a baby universe must be close to those of its parent, not wildly different. If every black hole produced a universe with completely random constants, there would be no heredity, no continuity from parent to offspring, and therefore no basis for evolution. On the other hand, if baby universes were absolutely identical to their parents, there would be no variation, and evolution could not happen. Natural selection requires variation to select from. Without variation, all universes would be the same, and there would be nothing to optimize. So we need a mechanism that produces small, random changes in the fundamental constants when a new universe is born from a black hole. Is there any reason to think such a mechanism exists? The answer is tentative but intriguing. The fundamental constants we measure, like the mass of the electron or the strength of the electromagnetic force, might not actually be truly fundamental. They might emerge from deeper underlying structures that could vary from one universe to another. In string theory, for example, the constants we observe are thought to be determined by the geometry of extra dimensions beyond the familiar 3 dimensions of space. String theory proposes that there are actually 9 or 10 spatial dimensions, but 6 or 7 of them are curled up into tiny shapes too small to detect directly. The exact shape and size of these extra dimensions determines what we perceive as the fundamental constants in our 4-dimensional space-time. Different configurations of the extra dimensions would produce different values for the electron mass, the strengths of the forces, and other parameters. There are an enormous number of possible configurations of these extra dimensions, perhaps 10 to the power of 500 or more. Each configuration corresponds to a different vacuum state with its own set of fundamental constants. This vast collection of possibilities is called the string theory landscape. Now, if the extreme conditions during black hole collapse and the subsequent bounce into a new universe could slightly alter the configuration of these extra dimensions, then the baby universe would have different fundamental constants from its parent. The key word here is slightly. The configuration would not be completely randomized because that would require an enormous amount of energy to traverse the entire landscape. Instead, the bounce might nudge the configuration to a nearby point in the landscape, similar to how quantum fluctuations or thermal noise can cause a system to hop to a neighboring state. This is exactly the kind of mechanism needed for cosmological natural selection. The baby universe would inherit constants close to those of its parent, but with small random variations. These variations would be the cosmic equivalent of genetic mutations. It is also possible that other features beyond the configuration of extra dimensions could vary during the birth of a baby universe. The topology of space, the number of dimensions, or other deep structural features might be determined during the quantum gravity phase of the bounce. Whatever the mechanism, the crucial requirement is that it produces heritable variation. Baby universes must resemble their parents more than they resemble random universes, but they must not be identical. There must be a concept of heredity, where properties are passed down through generations, and a source of variation, where new properties occasionally appear. If these conditions are met, then natural selection becomes inevitable. Universes with constants that favour black hole production will have more offspring. Those offspring will tend to have similar constants and will also produce many black holes. Over generations, the population of universes will evolve toward greater efficiency at black hole production. Let us walk through how this process would unfold over cosmic time. Imagine we start with some initial population of universes with a wide variety of fundamental constants. Perhaps these initial universes came into existence through some primordial process that we do not need to specify. They have random or semi-random values for their constants. Some of these universes will be terrible at making black holes. Perhaps their gravity is too weak to pull matter together into stars. Perhaps their nuclear forces are configured such that stars cannot ignite fusion. Perhaps they expand so rapidly that matter never clumps at all. These universes might make few or no black holes, and therefore they produce few or no offspring. Other universes in the initial population will be moderately good at making black holes. They can form stars, and some of those stars are massive enough to collapse into black holes at the end of their lives. These universes produce a moderate number of offspring. A few universes in the initial population might, by chance, have constants that are particularly well suited for black hole production. They efficiently produce heavy elements. They form many massive stars, and those stars reliably create black holes. These universes produce many offspring. In the next generation, the population of universes will be weighted toward those that came from prolific parents. The universes with good black hole producing constants will be overrepresented because they had many offspring. The terrible universes will be underrepresented because they had few offspring. This is not Darwinian competition in the usual sense. The unsuccessful universes do not go extinct. They still exist and continue to produce whatever small number of black holes they can manage. But they contribute less to the total population of universes in subsequent generations. Random mutations continue to introduce variation. Some baby universes inherit mutations that make them even better at producing black holes than their parents. Those universes become the new champions, producing the most offspring in their generation. Other baby universes inherit mutations that make them worse at producing black holes. They produce fewer offspring and contribute less to future generations. Over many generations, this process drives the population of universes toward configurations that are increasingly optimized for black hole production. The dynamics are similar to biological evolution, where populations gradually become better adapted to their environments through the accumulation of beneficial mutations and the winnowing out of harmful ones. Eventually, after countless generations, the typical universe in the population would be very good at making black holes. It might not be absolutely optimal because random mutations continue to introduce variation, but it would be much better than the initial random universes. This is where we might be today. If cosmological natural selection has been operating for an enormous span of time, perhaps infinitely long, then our universe should be a relatively fit member of the population, well optimized for black hole production. But is that actually the case? To answer that, we need to understand what makes a universe good at producing black holes. In our universe, black holes form primarily through the collapse of massive stars. When a star with a mass more than about 20 or 25 times that of the Sun exhausts its nuclear fuel, it undergoes a catastrophic collapse. The core compresses into a neutron star or black hole, and the outer layers are blasted away in a supernova explosion. So to maximize black hole production through this mechanism, a universe needs to maximize the number of massive stars that form and live out their lives. What does that require? First, you need matter to clump together to form stars in the first place. This requires gravity to overcome the pressure and kinetic energy of gas. The strength of gravity relative to other forces is therefore important. If gravity is too weak, matter will never collapse. If gravity is too strong, everything collapses immediately into black holes without forming stars first. Second, you need the gas to cool as it collapses. Hot gas has pressure that resists gravitational collapse. For a gas cloud to collapse into a star, it needs to radiate away energy and cool down. In the early universe, when the only elements present were hydrogen and helium from the Big Bang, cooling was very slow. The first generation of stars probably took a long time to form and were likely very massive. Modern star formation is much more efficient because the interstellar gas contains heavy elements from earlier generations of stars. Carbon and oxygen, in particular, form molecules like carbon monoxide that are excellent at radiating energy. These molecules cool the gas much more quickly, allowing stars to form more readily. So a universe that efficiently produces carbon and oxygen will be better at forming stars, and hence better at making black holes. This depends on the nuclear reaction rates in stars, which in turn depend on the fundamental constants governing the strong and weak nuclear forces. Carbon is produced in stars through the triple alpha process, where 3 helium nuclei fuse to form carbon. This process depends on a resonance in the carbon nucleus at just the right energy. If the strong nuclear force were slightly different, this resonance would not exist, and carbon production would be much less efficient. This is actually one of the most famous examples of apparent fine-tuning. The physicist Fred Hoyle predicted the existence of this carbon resonance in the 1950s precisely because carbon is abundant in the universe and there seemed to be no other way to produce it. The resonance was subsequently discovered experimentally, exactly where Hoyle predicted it should be. Oxygen production also requires a delicate balance. Oxygen is made by adding another helium nucleus to carbon. If this reaction proceeds too efficiently, all the carbon gets burned into oxygen and heavier elements. If it proceeds too slowly, there is not enough oxygen. The observed reaction rates seem to strike a good balance, producing both carbon and oxygen in useful quantities. Third, stars need to live long enough to produce heavy elements and eventually form black holes. The lifetime of a star depends on its mass and the efficiency of nuclear fusion. More massive stars burn through their fuel faster and have shorter lifetimes. The most massive stars live only a few million years before exploding. The timescale for nuclear fusion depends on the fundamental constants, particularly the strength of the weak nuclear force, which governs the reactions that initiate hydrogen fusion. If the weak force were significantly different, stars might burn out in thousands of years or take trillions of years to exhaust their fuel. Fourth, the star needs to be massive enough that its collapse produces a black hole rather than a neutron star. When a star explodes as a supernova, it leaves behind a compact remnant. If the remnant is below about 2 to 3 solar masses, it becomes a neutron star. If it is more massive, it collapses into a black hole. The cutoff mass depends on the equation of state of ultra-dense matter, which in turn depends on particle physics. This is where Lee Smolins' testable prediction comes in, and we will return to it shortly. So putting all this together, a universe optimized for black hole production via stellar collapse should have the following properties. It should have gravity strong enough to pull matter together, but not so strong that it overwhelms nuclear fusion. It should efficiently produce carbon and oxygen through stellar nucleosynthesis. It should have stars that live long enough to synthesize heavy elements and eventually collapse. And it should have a mass threshold for black hole formation that is low enough that many supernova remnants become black holes rather than neutron stars. Does our universe have these properties? To a large extent, yes. Our universe is quite efficient at producing carbon and oxygen. Stars have lifetimes ranging from millions to trillions of years depending on their mass, which seems reasonable. Gravity and the nuclear forces are balanced such that stable stars can exist for billions of years. Whether our universe is optimal or just pretty good is harder to say. To determine that, we would need to explore the entire landscape of possible fundamental constants and calculate how many black holes would be produced in each case. This is an enormously difficult task because it requires understanding star formation, stellar evolution, and supernova physics across a wide range of parameter values. Smolin and his colleagues have attempted to do this for some parameters. By varying constants one at a time or in small groups and using simplified models of stellar physics, they have tried to map out the fitness landscape. Their preliminary results suggest that our universe is close to a peak in black hole production, at least with respect to the parameters they examined. However, these calculations come with huge uncertainties. The models are simplified, and there may be effects they have not considered. It is possible that we are not near the true optimum, but only at a local peak, or that the true optimum is determined by factors beyond stellar black holes. This brings us to an important challenge raised by other physicists. Is stellar collapse really the dominant way that black holes are produced, or are there other mechanisms that might be more important? Cosmologist Alexander Vilenkin pointed out a potential problem with cosmological natural selection. He argued that if a universe lasts forever, the dominant mechanism for black hole production might not be stellar collapse, but rather spontaneous quantum fluctuations in the vacuum of space. According to quantum field theory, the vacuum is not truly empty, but rather a seething froth of virtual particles and fluctuations. Most of these fluctuations are tiny and short-lived, but quantum mechanics allows for arbitrarily large fluctuations, albeit with exponentially small probabilities. On very rare occasions, a fluctuation might be large enough to create a black hole directly from the vacuum. The probability of this happening in any given region of space, in any given time interval, is incredibly small. But if the universe lasts forever, these rare events will eventually happen everywhere. Vilenkin calculated that given infinite time, these quantum fluctuated black holes would eventually outnumber black holes formed from stars. This is because star formation is limited by the amount of matter available and the timescale for stars to form and evolve. Once all the matter has been processed into black holes, white dwarfs, and brown dwarfs, no more stellar black holes can form. But quantum fluctuations can continue forever. If Vilenkin is right, then universes should be optimized not for star formation, but for maximizing quantum vacuum fluctuations. This would favor universes that are as large and long-lived as possible. More space and more time means more opportunities for fluctuations to occur. What kind of universe maximizes volume and longevity? Probably one with a large positive cosmological constant causing rapid accelerated expansion. As the universe expands exponentially, the total volume grows without bound, creating ever more space for quantum fluctuations to happen. Our universe does have a positive cosmological constant driving accelerated expansion, but it is quite small. The expansion is accelerating, but not dramatically. If we were truly optimized for quantum black holes, we might expect a much larger cosmological constant. Smolin has responded to Vilenkin's objection in several ways. First, he points out that we cannot be certain the known laws of physics can be extrapolated to the incredibly long timescales required for quantum black holes to dominate. In 10 to the power of 100 years or longer, completely new physics might come into play that we have not yet imagined. Second, even if Vilenkin is correct that quantum black holes eventually dominate, this does not necessarily invalidate cosmological natural selection. It just means there are multiple branches of the cosmic evolutionary tree. Think of it as analogous to biological evolution on Earth. There are organisms adapted to many different ecological niches. Some bacteria thrive in hot springs. Some fish live in the deep ocean. Some mammals live on land. Each lineage has evolved to be well adapted to its particular environment. Similarly, there might be multiple cosmic niches corresponding to different black hole production mechanisms. Some universes are optimized for stellar black holes. Others are optimized for primordial black holes formed in the early universe. Still others are optimized for quantum vacuum black holes. We would naturally find ourselves in a universe on the stellar black hole branch, because that is the branch that produces heavy elements, long-lived stars, planets, and the conditions for life. The quantum black hole branch might be numerically dominant in the total population of universes, but we cannot exist there, so we do not observe it. This starts to sound a bit like the anthropic principle, which cosmological natural selection was supposed to avoid. But perhaps it is unavoidable. Even in an evolving multiverse, there may be multiple evolutionary pathways, and we can only exist on certain pathways. The advantage over pure anthropic reasoning is that cosmological natural selection provides a mechanism for why life-friendly universes exist, not just an assertion that they must. Another possible mechanism for black hole formation involves the very early universe. In the first fraction of a second after the Big Bang, before the universe had expanded and cooled very much, density fluctuations could have collapsed directly into black holes. These are called primordial black holes, and they could have masses ranging from tiny to millions of times the Sun. If density fluctuations were large enough in the early universe, primordial black holes could be abundant. They might even make up some or all of the dark matter that we detect gravitationally but cannot see directly. The formation rate of primordial black holes depends on the amplitude of density fluctuations, which is set by whatever process created those fluctuations. In inflationary cosmology, quantum fluctuations during inflation get stretched to cosmic scales and become the seeds for structure formation. The amplitude of these fluctuations depends on the parameters of the inflation model. If primordial black holes are the dominant type, then universes should be optimized for producing large density fluctuations in the early universe. This would require tuning the parameters of inflation or whatever mechanism generates the initial fluctuations. Again, this introduces additional complexity. A complete analysis of cosmological natural selection would need to consider all possible black hole formation mechanisms and determine which dominates in which regions of the parameter space of fundamental constants. Despite these complications, Smolin argues that the hypothesis makes at least one concrete, testable prediction that does not depend on knowing which mechanism dominates. This prediction involves the maximum mass of neutron stars. One of the key features that distinguishes science from mere speculation is testability. A scientific hypothesis must make predictions that can, at least in principle, be checked against observations. If the predictions turn out to be wrong, the hypothesis is falsified. Lee Smolin has argued that cosmological natural selection makes a concrete testable prediction about the maximum mass of neutron stars. When a massive star explodes as a supernova, the core collapses into either a neutron star or a black hole. Which one forms depends on the mass of the collapsing core. Below a certain threshold mass, the collapse is halted by neutron degeneracy pressure, the quantum mechanical effect that prevents neutrons from being squeezed too closely together. The result is a neutron star, a ball of neutrons about the size of a city with a mass of 1 to 2 times the Sun. Above the threshold mass, not even neutron degeneracy pressure can halt the collapse, and a black hole forms. The exact value of this threshold depends on the equation of state of ultradense matter, which describes how matter behaves at densities far exceeding that of atomic nuclei. Under normal conditions, matter is made of atoms, which are made of protons and neutrons, which are themselves made of quarks. Protons contain 2 up quarks and 1 down quark. Neutrons contain 1 up quark and 2 down quarks. But quarks come in 6 flavors: up, down, strange, charm, bottom, and top. Under the extreme conditions in a neutron star, it might be possible for some of the up and down quarks to convert into strange quarks, which are heavier but might be energetically favorable at high densities. If strange quarks form in the core of a neutron star, the resulting strange quark matter would be even denser than ordinary nuclear matter. This increased density would bring the star closer to the threshold for gravitational collapse. In other words, if strange quark matter forms, neutron stars would collapse into black holes at lower masses than if they remained pure neutron stars. The ease with which strange quarks can form depends on the mass of the strange quark. The lighter the strange quark, the easier it is to convert up and down quarks into strange quarks. A lighter strange quark means more strange quark matter forms, which means neutron stars are denser, which means they collapse at lower masses. If cosmological natural selection is true, then the strange quark mass should be optimized to maximize black hole production. since a lighter strange quark means more neutron stars collapse into black holes. We would expect the strange quark mass to be as low as possible, while still allowing stars to form and produce heavy elements. Lee Smolin calculated what the maximum neutron star mass should be if the strange quark mass is optimized in this way. He concluded that the cutoff should be around 2 solar masses. If the hypothesis is correct, there should be no stable neutron stars significantly more massive than 2 times the Sun. Any neutron star that massive would contain strange quark matter and would collapse into a black hole. This is a clear, testable prediction. All we need to do is measure the masses of neutron stars and see if any exceed the 2 solar mass limit. If we find neutron stars much heavier than 2 solar masses, that would be evidence against this version of cosmological natural selection. So what do the observations show? For many years, the most massive precisely measured neutron stars had masses around 1.4 solar masses, well below the predicted limit. This was consistent with Smolin's prediction, though it did not provide a strong test because neutron stars could have been more massive. As observational techniques improved, astronomers discovered more massive neutron stars. In 2010, a neutron star designated PSR J1 was found to have a mass of 1.97 solar masses, close to but still below the 2 solar mass threshold. This was encouraging for the hypothesis. However, in 2019, astronomers announced the discovery of an even more massive neutron star, PSR J0743 plus 6620, with a mass measured to be 2.17 solar masses. This is significantly above Smolin's predicted cutoff of 2 solar masses. More recent discoveries have found even heavier candidates. PSR J0952-0607 has an estimated mass of about 2.35 solar masses. PSR J1748-2021b in a globular cluster might be as massive as 2.5 solar masses. These observations appear to contradict Smolin's prediction. If the strange quark mass were optimized to maximize black hole production through the mechanism Smolin proposed, we should not see neutron stars this massive. However, there are some important caveats. First, mass measurements of neutron stars have uncertainties. The typical uncertainty is around plus or minus 0.1 to 0.2 solar masses, sometimes larger. It is possible that some of these objects are actually less massive than reported, though the most precisely measured ones seem to genuinely exceed 2 solar masses. Second, the predicted cutoff of 2 solar masses depends on assumptions about the properties of strange quark matter, which are not well understood. The calculations involve simplified models of the equation of state of ultra-dense matter. More sophisticated models might predict a somewhat different cutoff. Third, it is possible that strange quark matter does not actually form in neutron stars or forms only under certain conditions. If neutron stars remain ordinary nuclear matter rather than converting to strange quark matter, the mass limit could be higher. The existence of neutron stars above 2 solar masses might tell us about the physics of dense matter rather than about cosmological natural selection. Fourth, even if the prediction about strange quarks turns out to be wrong, this does not necessarily invalidate the entire framework of cosmological natural selection. It would just mean that the strange quark mass is not the parameter being optimized, or that stellar black holes are not the dominant type. The broader idea that universes evolve to favor black hole production could still be correct. Nonetheless, the discovery of neutron stars above 2 solar masses is at minimum a challenge to Smolin's specific prediction. It suggests that either the strange quark optimization idea is incorrect, or that there are additional complexities in the physics of neutron stars that the simple models do not capture. This is how science works. We make predictions based on theoretical ideas. We test those predictions against observations, and we refine or reject the ideas based on what we find. The existence of massive neutron stars does not prove cosmological. Natural selection is wrong, but it does suggest that if the hypothesis is correct, the details are more complicated than initially thought. Beyond the scientific questions of testability and observational evidence, cosmological natural selection raises fascinating philosophical issues. One issue is whether the theory really explains fine-tuning or just pushes the question back a step. The hypothesis says that our universe has life-friendly constants because those same constants favor black hole production, and universes evolve to maximize black holes. But this only works if there happens to be a correlation between black hole production and life-friendliness. Why should such a correlation exist? It seems to be a fortunate coincidence that the same elements that are good for cooling gas clouds and promoting star formation, carbon and oxygen, also happen to be essential for organic chemistry and life. If the optimal cooling mechanism involved different elements that had no role in biology, say beryllium and boron, then cosmological natural selection would produce universes full of stars and black holes, but with no particular advantage for life. In that case, we would still need some version of the anthropic principle to explain why we find ourselves in a rare universe where the black hole production mechanism happens to also support life. So cosmological natural selection might reduce the amount of fine-tuning that needs to be explained anthropically, but it does not eliminate it entirely. Smolin has acknowledged this point. He argues that the connection between black hole production and life-friendliness is not a complete coincidence, because both depend on similar underlying factors like long-lived stars and complex chemistry. But critics note that this connection is not inevitable, and other configurations might exist where they decouple. Another philosophical issue involves the nature of the multiverse implied by cosmological natural selection. If every black hole creates a new universe, and if our universe contains billions of galaxies each with millions or billions of black holes, then the number of universes grows explosively. In fact, the growth is not just exponential, but super exponential, because universes that are good at making black holes produce more offspring, leading to runaway growth. After many generations, the multiverse would be incomprehensibly vast, dominated by universes that are extremely efficient at black hole production. This raises deep questions about probability and what it means to be a typical observer. If there are 10 to the power of 1,000 universes or more, and most of them are highly optimized for black holes, then what does it mean that we find ourselves in a particular one? Should we expect to be in the most common type of universe? Or is our perspective inevitably biased by the requirement that we can exist? These questions connect to ongoing debates in cosmology about the measure problem in eternal inflation and how to calculate probabilities in an infinite multiverse. There are no universally accepted answers, and different approaches give different predictions. There is also the question of whether cosmological natural selection can explain increasing complexity over time. Biological evolution on Earth has produced organisms of stunning complexity through the accumulation of beneficial mutations over billions of years. Would we expect something similar in cosmic evolution? It is not obvious. The fundamental constants might evolve toward values that maximize black hole production, but this does not necessarily mean the universes themselves become more complex. If the optimal strategy for making black holes involved simple rather than complex structures, evolution might favor simplicity. On the other hand, if complex chemistry and long-lived stars are essential for efficient black hole production, as appears to be the case in our universe, then cosmic evolution might indeed favor increasing complexity. The presence of life, intelligence, and civilization could be seen as markers of a highly evolved universe in the cosmological natural selection framework. Some critics have raised more fundamental objections. They argue that the entire framework is too speculative to be considered science. We have no direct evidence that black holes create baby universes. We do not have a theory of quantum gravity that predicts this. The idea of cosmic mutations through changes in fundamental constants is plausible but unproven. Smolin's response is that speculation is an essential part of the scientific process. Major breakthroughs often come from ideas that initially seem wild or implausible. What matters is whether the ideas can be connected to testable predictions, even if the tests are difficult or indirect. He also notes that many widely accepted ideas in cosmology and theoretical physics are similarly speculative. The multiverse of eternal inflation, the landscape of string theory, the many worlds interpretation of quantum mechanics all involve entities and processes that cannot be directly observed. Yet these ideas are taken seriously because they address deep conceptual problems and make contact with established physics. Whether cosmological natural selection belongs in the same category is a matter of ongoing debate. Some physicists find it a compelling framework that deserves further development. Others view it as interesting but unlikely. Still others dismiss it as untestable speculation. The ultimate arbiter will be observational evidence and theoretical development. If future discoveries support the key predictions of the hypothesis, it will gain credibility. If observations continue to contradict it, or if alternative explanations prove more successful, it will fade away. Cosmological natural selection does not exist in isolation, but connects to many other ideas and debates in modern cosmology and theoretical physics. One connection is to the concept of the multiverse more generally. The idea that our universe is just one among many possible universes has been proposed in several different contexts. In eternal inflation, quantum fluctuations during an early period of rapid expansion create pocket universes with different properties. In the many worlds interpretation of quantum mechanics, every quantum measurement splits reality into multiple branches. In string theory, the vast landscape of possible vacuum states might all be realized somewhere. Cosmological natural selection offers a different mechanism for generating a multiverse, one based on black hole reproduction rather than inflation or quantum branching. But the underlying theme is similar. Reality is much larger than the observable universe, and what we see is just one small part of a vaster structure. Another connection is to theories of quantum gravity. The hypothesis critically depends on what happens at the center of a black hole when densities reach the Planck scale, where quantum gravity becomes important. Different approaches to quantum gravity, like loop quantum gravity, string theory, or causal set theory, make different predictions about whether singularities are replaced by bounces and whether new regions of space-time can form. As these theories develop and make more precise predictions, we may be able to evaluate whether the black hole baby universe scenario is plausible. This would not prove cosmological natural selection, but it would establish whether the foundational premise is at least possible. The hypothesis also connects to debates about the nature of the fundamental constants and whether they are truly fundamental or emerge from deeper principles. If the constants are fixed by some ultimate theory of everything, then they cannot vary, and cosmological natural selection cannot work. But if they are environmental variables determined by local conditions, similar to how the temperature and pressure are different in different places, then cosmic evolution becomes possible. There are also interesting parallels to biological evolution. Both involve populations, heredity, variation, and differential reproduction. Both produce apparent design through blind processes. Both can be studied using mathematical models of population dynamics and fitness landscapes. But there are also important differences. Biological evolution involves competition for limited resources, whereas cosmic evolution might not. Biological evolution operates on timescales of years to millions of years, whereas cosmic evolution involves timescales related to the formation and decay of black holes, potentially billions or trillions of years. Understanding these similarities and differences could deepen our understanding of evolution as a general principle applicable to many different kinds of systems, not just biological organisms. Finally, cosmological natural selection connects to fundamental questions about the nature of explanation in physics. What constitutes a satisfying explanation for why the laws of physics have the form they do? Is it enough to say that they follow from some deeper mathematical structure, or do we also need to explain why that particular structure exists? Some physicists believe that there must be a unique theory of everything that predicts all the fundamental constants with no free parameters. Others believe that some aspects of physics are environmental accidents that could have been different. Cosmological natural selection takes the latter view and adds an evolutionary mechanism to explain why the environment has the properties it does. These are deep and unsettled questions that go to the heart of what physics is trying to achieve. The debate over cosmological natural selection is in many ways a debate about these larger issues. More than 3 decades after Lee Smolin first proposed cosmological natural selection, where does the idea stand today? The hypothesis has not been widely adopted by the mainstream physics community. Most cosmologists continue to work within frameworks involving inflation, the anthropic principle, string theory landscapes, and other established paradigms. Cosmological natural selection remains a minority view pursued by Smolin and a small number of collaborators and sympathizers. Part of the reason for this limited acceptance is the highly speculative nature of the core premise. The idea that black holes give birth to new universes requires physics beyond our current understanding. We do not have a complete theory of quantum gravity that definitively tells us what happens at the center of a black hole. Until we do, the baby universe hypothesis remains in the realm of educated speculation rather than established science. Another factor is the difficulty of making precise, testable predictions. The prediction about neutron star masses was a bold attempt to connect the hypothesis to observations. But as we have seen, the discovery of neutron stars above 2 solar masses has cast doubt on that specific prediction. While there are ways to potentially reconcile the observations with the theory, the simple version of the prediction appears to have been falsified. Without clear observational tests that can distinguish cosmological natural selection from other explanations for fine-tuning, many physicists remain skeptical. The anthropic principle combined with the string theory landscape provides an alternative explanation that, while philosophically unsatisfying to some, does not require the additional assumption of black hole baby universes. However, the idea has not been definitively ruled out either. Recent developments in quantum gravity have actually lent some support to the possibility of black hole bounces creating new expanding regions. Loop quantum cosmology, a framework that applies the principles of loop quantum gravity to the universe as a whole, has shown mathematically that singularities can be replaced by bounces in certain models. These calculations are preliminary and involve many simplifying assumptions, but they demonstrate that the core idea is not obviously impossible. As our understanding of quantum gravity deepens, we may be able to make more definitive statements about whether black holes can create new universes. There have also been some interesting developments in thinking about how to test the hypothesis. Some researchers have explored whether there might be observable signatures of our universe having formed inside a black hole. For example, if we are in a rotating black hole, there might be preferred directions in space or subtle asymmetries in the cosmic microwave background. So far, observations show that the universe is remarkably uniform and isotropic, with no preferred directions, which is evidence against the simplest versions of the universe in a black hole idea. However, more sophisticated models might predict effects that are too subtle to have been detected yet. Another line of investigation involves trying to map out the fitness landscape more thoroughly. By using computer simulations of star formation and stellar evolution, researchers could potentially determine whether our fundamental constants really are close to optimal for black hole production. This is computationally challenging because it requires running realistic astrophysics simulations for many different sets of parameter values. If such calculations showed that small changes to the fundamental constants would dramatically increase or decrease black hole production, and if our universe turned out to be near a peak in the fitness landscape, that would be evidence supporting the hypothesis. Conversely, if our universe appeared to be far from optimal, that would be evidence against it. There is also ongoing work on understanding the physics of ultra-dense matter in neutron stars. Better models of the equation of state, including the possible formation of strange quark matter, could help clarify what the maximum neutron star mass should be under different assumptions. This could either vindicate or further challenge Smolin's prediction. Looking forward, several developments could significantly impact the status of cosmological natural selection over the coming decades. First, advances in quantum gravity theory might tell us definitively whether black holes can create baby universes. If a complete theory of quantum gravity predicts that singularities are replaced by bounces that create new expanding regions, that would establish the plausibility of the foundational premise. If quantum gravity predicts that singularities are not replaced by bounces, or that the interior of a black hole cannot create an expanding universe that would undermine the entire framework. Second, continued observations of neutron stars will provide more data on the maximum mass. If additional neutron stars are discovered with masses well above 2 solar masses, say 3 solar masses or more, that would increasingly strain the strange quark optimization prediction. On the other hand, if improved measurements show that the most massive objects are actually closer to 2 solar masses, or if a clear cutoff is observed, that could revive the prediction. Third, advances in computational astrophysics might make it possible to thoroughly explore the fitness landscape and determine whether our universe really is close to optimal for black hole production. This would require running detailed simulations of galaxy formation, star formation, and stellar evolution across a wide range of parameter values. The calculations would be demanding, but computing power continues to grow exponentially. Fourth, observations of the early universe might provide clues about whether primordial black holes are abundant and whether they could be a dominant form of black hole production. Gravitational wave detections, studies of the cosmic microwave background, and searches for gravitational lensing effects could all contribute to understanding whether primordial black holes exist in large numbers. Fifth, the search for life elsewhere in the universe could provide indirect evidence about how common life-friendly conditions are. If we discover that life emerges readily whenever liquid water and organic chemistry are present, it would suggest that the fundamental constants are indeed well suited for life, consistent with cosmological natural selection. If life turns out to be extraordinarily rare, despite apparently favorable conditions, it might indicate that the connection between black hole production and life is weaker than the hypothesis suggests. Finally, continued theoretical work on the connections between cosmological natural selection and other ideas like eternal inflation, the string landscape, and the anthropic principle might reveal new insights or testable predictions. Perhaps cosmological natural selection could be embedded within a larger framework that combines multiple mechanisms for generating multiverses. It is worth emphasizing that even if cosmological natural selection turns out to be wrong in its specifics, the exercise of developing and testing the hypothesis has value. It has stimulated thinking about how to explain fine-tuning without invoking pure anthropic reasoning. It has highlighted connections between cosmology and evolutionary biology. It has raised important questions about testability and what counts as scientific explanation. Science progresses not just through the ideas that turn out to be correct, but through the entire process of proposing hypotheses, working out their implications, and testing them against reality. Many ideas that seemed promising turn out to be wrong, but they contribute to the collective understanding by ruling out possibilities and pointing toward more fruitful directions. Whether cosmological natural selection represents a genuine insight into the nature of reality or an interesting but ultimately incorrect speculation remains to be seen. The coming decades of observations and theoretical developments will hopefully provide clearer answers. Stepping back to consider the big picture, cosmological natural selection is part of humanity's long-standing quest to understand why the universe exists and why it has the properties it does. Throughout history, different cultures and thinkers have proposed various answers to these fundamental questions. Ancient mythologies often describe the universe as created by gods or emerging from primordial chaos. Medieval philosophers and theologians developed sophisticated arguments for a necessary being that grounds all contingent existence. The scientific revolution brought a new approach to understanding nature based on observation, experiment, and mathematical law. Scientists discovered that the universe operates according to regular patterns that can be described with remarkable precision. Newton's laws of motion and gravity, Maxwell's equations of electromagnetism, Einstein's theory of relativity, quantum mechanics, each revealed deep mathematical structures underlying physical reality. Yet even as we have uncovered these laws, we continue to face the puzzle of why these particular laws and not others. Why does nature follow mathematical patterns at all? Why do the fundamental constants have the specific values we measure? Why does the universe appear to be fine-tuned for complexity and life? Some physicists hope that a final theory of everything will explain why the laws of physics must be exactly as they are, with no free parameters or arbitrary choices. String theory has been pursued as a candidate for such a theory, though it has not yet achieved the goal of making unique predictions. Others believe that some aspects of physics are environmental rather than fundamental. Just as the temperature and atmospheric pressure are different on Earth versus Mars, perhaps the fundamental constants are different in different regions of a larger multiverse. If so, the question shifts from why the constants have the values they do everywhere to why they have the values they do in our particular region. The anthropic principle takes this further by noting that we can only exist in regions with life-friendly constants, so it is not surprising that we find ourselves in such a region. But many find this explanation unsatisfying because it seems to give up on finding a deeper reason for the observed properties. Cosmological natural selection offers a middle path. It accepts that the constants might be environmental variables that differ across the multiverse, but it adds an evolutionary mechanism that explains why life-friendly values are not just possible, but probable. Universes evolve to maximize black hole production, and this incidentally favors life-friendly conditions. This explanation is more satisfying to some because it provides a natural, mechanical process, rather than appealing to luck or selection effects. It is similar to how Darwin's theory of evolution explained the apparent design in biology without requiring a designer. Random variation and differential reproduction naturally produce organisms that appear designed for their environments. Whether or not cosmological natural selection is correct, it illustrates an important point about scientific explanation. The universe we observe is the result of processes operating on many different scales, from the quantum realm to the cosmic scale, from brief moments after the Big Bang to billions of years of cosmic evolution. Understanding the universe requires connecting these different scales and time periods into a coherent picture. The fundamental constants might be set by quantum gravity processes in baby universe formation. Those constants determine how stars form and evolve. Stellar evolution produces the heavy elements needed for planets and life. Life emerges and evolves on those planets over billions of years. Each level builds on the ones before, and each involves both law-like regularities and contingent accidents. The interplay between law and chance, between necessity and possibility, is what makes the universe rich and interesting. Perhaps the most profound implication of cosmological natural selection is that we might be part of a process much larger and longer than we previously imagined. Our universe is not a static, finished product, but potentially one node in an evolving network of universes stretching back through countless generations. If this is true, then every black hole we observe might be a seed of new cosmic possibilities. Every massive star that explodes might eventually give rise to entire new universes with their own stars, galaxies, and perhaps their own forms of life and intelligence. This perspective is simultaneously humbling and awe-inspiring. Humbling because it suggests we are an infinitesimal part of an incomprehensibly vast multiverse. Awe-inspiring because it connects us to a grand cosmic process that links everything that has existed, everything that exists now, and everything that will exist in the future. If cosmological natural selection is correct, what does it imply about the future of life and intelligence in the universe? In our universe, life emerged on Earth about 3.8 billion years ago, roughly a billion years after the planet formed. For most of Earth's history, life consisted only of simple single-celled organisms. Complex multicellular life appeared only in the last billion years. Intelligent life capable of understanding the universe and asking these deep questions emerged very recently, within the last few 100,000 years. This timeline suggests that the emergence of intelligent life requires billions of years of planetary evolution. It requires a stable star providing steady energy. It requires a planet with the right temperature range for liquid water. It requires complex chemistry based on carbon and other heavy elements. All of these conditions trace back to the fundamental constants of physics. If our universe is optimized for black hole production through stellar collapse, then it is also optimized for producing the conditions needed for life. Long-lived stars, abundant heavy elements, stable planetary systems all follow naturally from a universe tuned for star formation. But the optimization is for star formation in general, not specifically for life. The universe makes trillions of stars, but only a tiny fraction of them might have planets with life. An even smaller fraction might develop intelligent life. And perhaps only a vanishingly small fraction develop technological civilizations capable of understanding cosmology and asking about the origin of the universe. From the perspective of cosmological natural selection, intelligent life is an epiphenomenon, a side effect of optimization for black holes. The universe does not care whether we exist. It is not optimized for our benefit. We exist only because the same conditions that favor black hole production happen to also allow for complex chemistry and biological evolution. This is similar to the situation in biological evolution. Natural selection optimizes organisms for survival and reproduction, not for happiness or self-awareness. Consciousness and intelligence evolved in some lineages because they happened to be useful for survival, not because evolution was aiming for them. Yet despite being cosmic accidents, we find ourselves in a remarkable position. We are matter that has become aware of itself. We are the universe observing and understanding itself. Through billions of years of cosmic and biological evolution, the atoms forged in ancient stars have been assembled into structures capable of contemplating their own origins. What might the future hold? If intelligent life is common in the universe, then there could be many civilizations scattered among the stars, each trying to understand the cosmos and their place in it. Some might be far more advanced than us, having survived for millions or billions of years. Such advanced civilizations might develop technologies we can barely imagine. They might be able to manipulate black holes, harness the energy of entire stars, or even influence the fundamental constants in their region of space. They might create artificial black holes and thereby spawn new universes, becoming cosmic gardeners cultivating the multiverse. On the other hand, intelligent life might be extremely rare. We might be alone in our galaxy or even in the observable universe. The steps from simple chemistry to life, from simple life to complex life, from complex life to intelligence, might each be improbable enough that they rarely occur even in a universe with trillions of stars. If we are rare or unique, that places an even greater weight of significance on our existence. We might be the only way this region of the multiverse can come to understand itself. The questions we ask and the answers we discover might be unique contributions to the cosmic story. Looking billions of years into the future, the universe will continue to evolve. Stars will continue to form from remaining gas clouds, though at a declining rate as the gas gets used up. Existing stars will age and die, some exploding as supernovae and forming new black holes. Galaxies will collide and merge. Black holes will grow by consuming matter and merging with each other. Eventually, perhaps in 1 trillion years or more, star formation will cease entirely. The universe will enter an era dominated by slowly fading white dwarfs, dead neutron stars, and black holes. The black holes will continue to grow for a while, but eventually they will begin to evaporate through Hawking radiation, a quantum process that causes black holes to slowly lose mass. If cosmological natural selection is correct, each of these black holes, before it evaporates, might give birth to one or more baby universes. Those baby universes would enter their own cycles of expansion, star formation, black hole production, and eventually decline. And those baby universes would spawn their own offspring. So even as our universe grows old and dark, the multiverse would continue to flourish and grow. The torch of cosmic evolution would be passed on to new generations of universes, each building on the successes of its ancestors. From this perspective, the meaning of our existence is not found in being the center of creation or the purpose of the universe. Instead, it is found in being part of an ongoing process, a link in an infinite chain connecting past and future, a brief moment of awareness in the eternal dance of cosmic evolution. To fully appreciate cosmological natural selection, it helps to understand the other ideas that have been proposed to explain fine-tuning and the nature of the multiverse. The theological perspective holds that the universe was designed by an intelligent creator who intentionally set the fundamental constants to values that would allow for life. This explains fine-tuning directly. The universe is fine-tuned because it was tuned by God. Many religious believers find this explanation satisfying and see the apparent design in nature as evidence for the existence of a creator. From a scientific standpoint, the problem with the design hypothesis is that it does not explain where the designer came from or why the designer chose the particular values observed. It also does not make testable predictions about what we should observe beyond what we already know. For these reasons, most scientists prefer naturalistic explanations that do not require supernatural entities. the many worlds interpretation of quantum mechanics suggests that every quantum measurement causes reality to branch into multiple versions, with each possible outcome occurring in a different branch. If this is correct, there is a vast multiverse of quantum branches, and different branches might have different effective laws of physics if those laws are influenced by quantum outcomes. This provides a form of multiverse that could potentially explain fine-tuning through anthropic selection. However, most versions of quantum many-worlds do not actually predict variation in fundamental constants across branches, only variation in contingent facts about particle positions and quantum measurements. Eternal inflation, a leading cosmological paradigm, proposes that the early universe underwent a period of exponentially rapid expansion, driven by a scalar field called the inflation. In some regions, inflation ended, and those regions became universes like ours. But in other regions, inflation continued. Because inflation expands space faster than it decays, the total volume of inflating space grows without bound, continually spawning new bubble universes. In eternal inflation combined with the string theory landscape, different bubble universes might settle into different vacuum states with different fundamental constants. This creates a vast multiverse in which all possible values of the constants are realized somewhere. We find ourselves in a bubble with life-friendly constants because we could not exist in the others. This is currently the most popular framework among cosmologists for thinking about the multiverse and fine-tuning. It has the advantage of being connected to well-studied theories like inflation and string theory, even though both involve speculative elements. The main criticism of eternal inflation plus anthropic selection is that it seems to give up on finding a deeper explanation. It says we observe these particular constants simply because we happen to be in a bubble with those values, and we could not be anywhere else. There is no mechanism to explain why life-friendly bubbles exist, only an assertion that if bubbles with all possible constants exist, some must be life-friendly. Cosmological natural selection offers an alternative that avoids this purely anthropic reasoning. It provides a mechanism, cosmic evolution through black hole reproduction, that actively favors the emergence of life-friendly constants rather than treating them as lucky accidents. Another perspective is to question whether fine-tuning is really as severe as often claimed. Some physicists argue that the apparent fine-tuning might be an artifact of how we think about varying the constants. When you change one constant, it might be necessary to change others to maintain consistency, and when these interdependencies are taken into account, the range of life-permitting values might be larger than naive calculations suggest. Others point out that we only have one example of life on Earth, so we do not really know how flexible the requirements for life are. Perhaps very different forms of life could exist under different physical constants. If so, a much wider range of universes might be life-permitting, reducing the fine-tuning problem. These arguments are ongoing, and there is no consensus about whether fine-tuning is a real problem requiring explanation or an illusion arising from our limited perspective. But for those who believe fine-tuning is real and requires explanation, cosmological natural selection offers an intriguing alternative to pure anthropic reasoning. There have also been various proposals for modified versions of cosmological natural selection. Some researchers have suggested that civilizations, rather than black holes, might be the reproducing entities. Advanced civilizations might develop technology to create baby universes, and universes would evolve to favor conditions that produce advanced civilizations. This would create a more direct connection between cosmic evolution and the emergence of intelligent life. Other modified versions suggest that universes might reproduce through mechanisms other than black holes, such as through quantum tunneling events or through some as yet unknown process. The key idea would still be heredity and variation leading to evolution, but the specific mechanism would differ from Smolin's original proposal. All of these ideas remain speculative, and it is possible that the correct explanation for fine-tuning, if there is one, has not yet been imagined. The landscape of ideas is still being explored, and future observations and theoretical developments will hopefully narrow down the possibilities. Cosmological natural selection represents science operating at the edge of the known, venturing into territory where direct observation is difficult or impossible, and where theoretical frameworks are incomplete. This is both the strength and the weakness of the idea. The strength is that it addresses profound questions about why the universe has the properties it does, and it does so using concepts drawn from successful scientific theories like general relativity and evolutionary biology. It makes a genuine attempt to provide a naturalistic explanation for apparent cosmic design. The weakness is that many of the key premises are unproven and perhaps unprovable. We do not know that black holes create baby universes. We do not know that fundamental constants vary in those baby universes. We do not know that our universe is optimal for black hole production. Each of these assumptions requires leaps beyond established physics. Yet speculation beyond the known is how science progresses. Every major breakthrough in physics began with ideas that seemed wild or implausible at the time. Heliocentric cosmology contradicted common sense and scripture. Relativity violated cherished notions about absolute space and time. Quantum mechanics defied classical logic and determinism. The Big Bang was initially ridiculed as too fantastic to be taken seriously. In each case, what elevated these ideas from speculation to accepted science was a combination of theoretical coherence, mathematical rigor, and most importantly, observational confirmation. The ideas made predictions that could be tested, and when tested, they were found to be correct. Cosmological natural selection has theoretical coherence. It connects concepts from general relativity, quantum gravity, and evolutionary biology into a logical framework. It has made at least one concrete prediction about neutron star masses, though the verdict on that prediction is not favourable. The question is whether future developments will provide additional tests and whether the hypothesis will pass those tests. In the meantime, the value of cosmological natural selection lies not just in whether it is ultimately proven correct, but in how it expands our thinking about what is possible. It shows that there are alternatives to the anthropic principle for explaining fine-tuning. It demonstrates how evolutionary thinking can be applied beyond biology. It raises deep questions about the nature of explanation in physics and cosmology. For those working on the idea, the goal is to continue developing the framework, making it more precise, finding additional testable predictions, and connecting it to other areas of physics. For the broader community, the goal is to keep an open mind while maintaining appropriate skepticism, evaluating the idea on its merits as evidence accumulates. Perhaps decades or centuries from now, cosmological natural selection will be recognized as a profound insight into the nature of reality, as important as evolution by natural selection was for biology. Perhaps it will be remembered as an interesting but ultimately incorrect idea that stimulated useful thinking. Or perhaps the question will remain unsettled, one of many competing frameworks for understanding why the universe has the properties it does. Whatever the outcome, the journey of exploring these ideas is worthwhile. Every time we push against the boundaries of knowledge, asking questions about the deepest nature of reality, we honor the best impulses of human curiosity and creativity. We are creatures who wonder why we exist and where we came from. Science is our most successful tool for addressing those questions. The idea that every black hole might be creating new universes, that our cosmos might be just one node in an infinite network of evolving realities, is stunning to contemplate. It vastly expands our conception of existence and our place within it. Whether or not it is true, it reminds us that reality might be far stranger and more wonderful than we ever imagined. As we look up at the night sky and see the stars scattered across the darkness, we can wonder whether we are seeing not just distant suns, but potential doorways to other universes. We can wonder whether the black hole at the center of our galaxy has already given birth to countless cosmic offspring. We can wonder whether we are the product of billions of years of cosmic evolution, shaped by the same forces that drive biological evolution here on Earth. These questions remain open. The answers await future observations, theoretical breakthroughs, and perhaps generations of scientific work. But the questions themselves illuminate our remarkable position as conscious beings trying to understand the universe that gave rise to us. And in that quest for understanding, in that reaching out to grasp the deepest truths about existence, we express something essential about what it means to be human.